The design, build and test project is the first real hands-on experience of research that the first year CDT will have. The understanding how to conduct research not only on a theoretical level but also on a practical level. So this is what I see being the role of the design, build and test course. The challenge is growing up. I mean, the challenge is growing up and start to behave like a researcher and instead of as a student. I mean, in Italy we would say stop expecting the ready meal and start to cook it yourself, probably.
Doing research on the ground, making the mistakes, is arguably invaluable, particularly given you're about to do a 3-year PhD.
I think the project is one of the highlights of the CDT, and we'd always had really good feedback from previous years.
It's very nice to work with a large group of people, mostly because most of us have different backgrounds, so it's a very good mix of people to work with.
It's giving us the opportunity to have hands on a proper experiment ahead of our PhD project.
So this year we are substantially creating a demonstrator for one of the research activity that is going on in BCI. And the project is a structural project. It's substantially a cylinder under compression with a side load. And we will use the results to predict the buckling of the structure.
There's been experiments that have been conducted to study the stability of cylinders, but most of them are based on isotropic materials. So what we are doing is applying an axial load on the cylinder, and at this axial load apply a lateral poking force that would kind of induce the buckling and see at what point the cylinder is going to buckle. So the aim of this is to come up with a stability plot that would then be used to predict the buckling stability of composite cylinders.
There's not a lot of literature available for composite cylinders. There was a paper that looked at an aluminium can and used the same method, so probed that to find the buckling load of the can. So we tried to recreate the geometry of the can on the FEA model. So initially we needed to model different layups and different materials to give the manufacturing team information in terms of the buckling load. We also needed to make a perfect cylinder model to test our actual modelling method.
So I'm part of the manufacturing team, so we are essentially making the cylinder. Our job is to manufacture the cylinder as perfect as possible. Obviously that's not going to be the case. There's going to be defects and imperfections introduced, hopefully not too many.
We first had to work out how we were going to actually physically lay up these plies and then curve them around our mould. We already had our cylindrical aluminium tool. Its length was 750 millimeters, which meant that we could get 2 cylinders on the tool at the same time.
So my team's task is divided into 2 main objectives. The first part is to actually design the testing rig. So a rig that can actually apply this axial load, measure it, and then apply the poking force and measure that one as well. And then to actually conduct this test.
There are no books at all not to design a machine in general, but especially there are no books to design a machine for a test that no one has ever done.
The CAD designs and bringing together all those mechanical engineering related things, that's not my field. But fortunately we have an expert in mechanical engineering who really likes doing these things.
In order to get an accurate result, we need to design a test rig that have a step size of 1 micron and moves in only one direction. We need to collaborate very closely with the other group because we have some very important parameters that all the groups need to agree with. For example, the diameter of the end cap of the cylinder. It takes a lot of time to modify our design.
we're not yet experienced hand layup operators, so that's going to be a big challenge, like laying up very thin carbon fibre prepreg around a cylinder. So actually, I don't think we'll realise kind of what challenge that is until we get in the lab and start doing it ourselves.
So we paired the plies up in terms of their fibre direction. Pairing the like fibres together meant that the cuts of prepreg were all the same dimensions. So after we'd laid up 2 cylinders onto the aluminium tool, we then had to bag it, which did involve rolling the tool along the table. And from there, it went into the autoclave. Once we had 2 cured cylinders, we went into potting, which did involve applying epoxy rings around each end of the cylinder. And one of the issues that we encountered with that is getting the cylinder completely centered within the mold. So to do that, I designed and manufactured some arms that would perfectly hold the outer diameter of the cylinder in place. I would say our work was very front-loaded. The testing team can't do their main job until we've done our job, and likewise for modelling.
So the next step was characterising the imperfections in the manufactured cylinders. So we used a 3D scan to give us a cloud of data points for the outer surface of the cylinders. So once the imperfection signature is in the FEA model, we're then able to simulate the actual experiment that the testing team are going to do. So we can give them data such as where to apply their strain gauges based off where the cylinder is weakest and most likely to buckle. And also we'll be able to tell what a theoretical buckling load of this exact cylinder that we've manufactured should be before they take it to testing as well.
When we sent the original design to the workshop, they said we don't have enough material, we need to order it and it's going to take a lot of time. We find some scrapped aluminium from a basement and we change our design based on what material we have. It do the job and the result is pretty good. Our final test is in 2 weeks and now we have all the mechanical parts ready.
I do a lot of Kirby's during the testing, which improved my entertainment. I ended up with like 20 Kirby's. Originally, the steps were 5 minutes each, so the instrument would move like in 0.1 millimeters at a time and then will hold for 5 minutes. So it gave plenty of time to draw.
At first, actually, in the literature, they designed the experiment with force control, but due to the safety reason, we changed to displacement control. So we didn't want it to like crush the specimen.
Yeah, the machine gun load, which is fascinating and bizarre and definitely bad.
What we managed to figure out, as it was going down in displacement control, the instrument caused it to buckle, which caused the cylinder to contract a little bit, making it think that it's gone way too far down in the displacement, so it would reset, it would just get caught in a feedback loop, which was terrifying. Yeah, I would say we got pretty decent results. Overall, I'm quite satisfied with what we got.
We spent the last couple of days interpreting the data, creating stability landscapes and comparing those to the results that we got from the FEA modelling. It kind of matches within reason. It's, there's something there to work with. It's hinting that we're on the right tracks.
I feel like we worked together pretty well as a team. I think it was useful to sort of get to know the technicians on a little bit of a more personal basis, so that if you ever need to like talk to them going into your PhD, you know who to go for advice.
I would say one of the most important things I've learned is to kind of be more flexible with what you expect of an experiment. Like, things will and probably can go wrong very easily. Things will always take more time than you think.
I think if we had this chance to do it again, we would spend much more time on the planning the experimental procedures and do it better.
For me, it was all quite a large learning experience, but it's been good. It's something I knew that I needed for the PhD.
They had a good first attempt at modelling work, especially if they don't have that much experience with the software. They got to grips with it pretty quickly.
Yes, it's about building and testing it and seeing the results, but the real things you take away from it are how you work with people and how you go around interacting and planning, more so than the actual making and testing of it. And I think in that regard they've done a fantastic job.
They did better than what they think. They did better than what they think. No, I mean, they did very good. They showed that they are understanding the problem. They showed that they put their brain into it and in trying to come up with solution. Yeah, again, not only learning from the book, learning from experience.